Okay, so I think we're good to go. So in terms of what's all due coming up, the big one is programming assignment 2, due at the end of the week. So how are we all doing on that? Who's all done? A few. That's good. Who's done with the exception of hash table? Another set. Who's done with the exception of hash table and find cycle? That's good. So all of this, I think, is relatively doable. Who hasn't at least done through maybe the first 3 parts? Right. So better get working on it. Again, nothing fundamentally new about programming assignment 2, right? It's essentially mastering using pointers and allocation and dereferencing to build data structures. Any kind of quick questions about programming assignment 2? Logistics questions. I saw a hand just now. Right. Well, yeah.
For problems for methods 1 through 3, if I just use the adjacency matrix instead of going to the adjacency matrix, is that fine?
Yeah. So we provide. Well, we'll take a quick look at kind of the infrastructure for the programming assignment later in a couple minutes. Just to point out some features along the way. Yeah, you can choose to use the given graphutils adjacency list storage, or you could load it whichever way solves the problem. And then looking just beyond that, so programming assignment 2 due at the end of the week. And then quiz 4 will be coming along shortly after that. We're on a schedule where quizzes are due on Wednesday, so not tomorrow, but the Wednesday in a week, so 8 days from now, that'll be quiz 4 is due. So quiz 4, wait, is that correct, or am I confused? Quiz 4, when is quiz 4 due? Tomorrow. Okay, so well, yeah, so that's the correct timing, right? Quiz 4 really is, again, pretty straightforward. If you've been working on programming assignment 2, it's all the pointers and memory stuff, the kinds of bugs that you might see writing pointers and memory code. And then it's all about bits and bytes, right? So these operators, the ands and ors and bitwise XORs and bitwise nots, and how integers work, storing numbers in C, all that is covered in quiz 4. What we'll do now is just take a quick kind of tour around what you've been seeing in programming assignment 2, right? So this is not like a quick start on programming assignment 2. Most of you have already been working on PA2. But this is just to point out some interesting things in the PA2 package. So, right, PA2. Based on what you've been working on so far, the first piece is very straightforward, right? This is just getting familiar with how to use the provided code. The underlying message here, or the underlying thing to learn here, is an example of how to organize code so you can reuse code whenever possible, right? The reason I extracted graphutils and gave that to you as a header is that we've got 5 pieces of the assignment which all rely on something similar, so that function has been pulled out into a shared header that you can reuse in a lot of different parts of the assignment. The rest really is just a repeated practice on using stacks and queues, depth first search, breadth first search, depth first traversal, breadth first traversal. All of this is review from data structures. And really the last piece as well, hash table, is also a linked list, is also a practice on using linked lists. Yeah, question?
For 2, it says you need either DFS or BFS, but don't you not need them?
There's several ways, right? So if you look for algorithms for detecting whether or not a graph has cycles. What are some ways to implement that? Yeah.
For example, like because it's a non-directed graph, right? Like for non-directed graphs, like just if the number of like connections is greater than like the number of nodes, it has a cycle.
That could be a useful heuristic, sure. I think there may be some exceptions to that. I have to think about whether that's a valid implementation. So it could be pass. It could pass the test cases we give, though.
Like the auto grader, like different auto graders didn't work.
Okay. Very good. Right. So let's take a quick look at some gotchas. Right. So one gotcha, based off of what I've seen on the Piazza and on discussions, is that this assignment plays around with multiple representations of graphs. So the first part, edge list. This is, keep in mind, a adjacency matrix representation. So how do we read an adjacency matrix? Let's use a slightly more involved case, test case 1 here. How do you read the adjacency matrix? How do you interpret the adjacency matrix? Yeah. So, okay, what edges do we have? How many edges do we have in this graph? Assuming that this is a undirected graph, yeah. 4. How do you read off the 4?
Like from, I'm gonna like say like row 2 is like index 0 for like the rows columns. It's like node, like the first row is like for node 0 is connected to node 1, node 2, and node 3.
Yeah, so we have edges 0 to 1, 2, and 3, and then we have an edge from 1, this being the second row down, index 1, to the last node, node 3. This is an undirected graph, so what's an important property about this matrix? Let's use our fancy linear algebra matrix math terms here. Yeah. Symmetric. What does symmetric mean? Is it symmetric down a vertical axis?
I think it's symmetric down the y equals x axis.
It's symmetric down the y equals x axis, so it's symmetric down the diagonal. So if you took this matrix and you flipped it across this diagonal, it's the same matrix, right? It's, in other words, it's also called self-transpose. It is equal to its transpose. Another term for self-transpose is that this is a symmetric matrix. What if a graph representation is not symmetric? What does that entail?
That's the directed graph.
It has to be a directed graph, right? So what does it mean for a graph to be directed? Yeah. So you can have edges that have directionality. Edges can be from 0 to 1, but that doesn't entail 1 back to 0 is connected, right? So here in this assignment, we've got these undirected graphs, we've got directed graphs. So in the directed graph, so which examples here do we use a directed graph? Right, of the pieces of the assignments that we've got, where should I go to find an example of directed graph? Yeah. MST, is that a directed graph? Yeah. Yeah, find cycle, I think, we should double check, right? There's something special about the MST graph too, but we'll get to that. The find cycle part will have directed graphs, so you can take a look. Right, so we've got directed graphs here. You kind of have to zoom in to see the arrows that the graphs have direction. So here, 0, 1, and 1, 0 are connected to each other. So this is directed, but the one edge has both directions associated with it. Here we have something that is still a directed graph. This is 0 is connected to 1, 1 is connected to 2, 0 is connected to 3. For all those edges, the bidirectionality is also implied. Let's see if we can find a first useful example here. Right, so here we have a little bit more involved graph, right? So here finally we have an example where 1 is connected to 2, but 2 back to 1 is missing that arrow. So we can see this, right? 1 should be connected to 2, 2 is not connected to 1. And 2's row is here, right? So we see, 2's row is this one. So 2 to 3 is not connected, but then the other case, 2 down to, let's see, 2, hold on, let's correlate what we're seeing here with the picture here. All right, so what I want to focus on is node 1 to node 2, right? Node 1 to node 2. So this is row 1, column 2, and also column 1, row 2. We should see 1, 0 in one, and a 0 in the other, right? The directionality is only one such direction. So let's go to row 1. This is row 1, column 2. We see the 1 there. But then column 2, this is column 2. If we go down to row 1, sorry, we go down to row 1, column 2, row, hold on, I'm messing this up, right? So row 1, column 2, there's the 1. Column 1, row 2, this one here, right? So notice how this 0 here and this 1 here, they're in transposed position. So what I was trying to point out is that one of the rows, one of those elements is 1, and while the other is 0, right? So this is a directed graph where the two directions are not equivalent. Quick thing, right? So we talked about transpose. What happens, what does it mean to transpose this matrix? What would that represent? Yeah. So we switch the rows and columns. So transpose, if we did the same task, right? We take the diagonal and we flip it over. In this case, this matrix is not self-transposed, as I just pointed out with that example already, right? So not self-transposed, but what is implied by the transpose? Yeah. Yeah, it would basically come into this picture here and take all the arrows and flip the direction of all the arrows, right? This is kind of a preview. You know, later on in the semester, we'll have other problems we have to do transpose. What is another interesting thing we can examine here? So we talked about MST, the minimum spanning tree or maximum spanning tree piece. There's something interesting going on about the graphs here, right? So for these, the edges are associated with weight. So this is now no longer an unweighted graph, but rather a weighted graph. So each of these edges have weights associated with them. And you know, the representation we've been using so far is the adjacency matrix. And in this adjacency matrix representation, we can easily encode the weights, again, by just replacing 0, 1, a Boolean, with a floating point value indicating the weights. So same thing still, right? These graphs, directed or undirected? Yeah, undirected, so they're still self-transposed. You'll see that this is equivalent to that. And you'll see that for the rest of the test cases. A kind of unfortunate thing is these labels are somewhat jumbled up. The definitive source of which weight is associated with which edge comes from the file, right? So the file is correct. But if you try to study this and take a very close look at the picture, these labels kind of float around in the picture. They're not necessarily stamped upon the exact edge that they're supposed to be. And this is especially true as you get to larger graphs, right? The NetworkX plotting package is not so good at automatically getting these to plot nicely. So again, the test case files will be the definitive source. Okay, so that's just studying the representation. What are various ways we can represent graphs, right? So graphs, we've studied them in data structures plenty now. So what are common ways to store graphs? Yeah. Good, right? So adjacency matrix, which we've seen already. Edge list. So what is the edge list representation?
That's what we did in part 1, right? For non-directed. And for directed, it would just be, we just go through the adjacency matrix and find like each one, like there's a 1 or a weight in the rows.
So the edge list is just the list of edges, right? So every time you see a valid edge, write down the source node and the target node. Perhaps the kind of trickiest one, finally, is adjacency list. What's the encoding for adjacency list? Yeah.
It's like a list of lists where each, like the first, I guess each list is a list of all of the nodes that are connected to a specific index in the larger list.
Yeah, so it's a list of lists, right? So it's a representation where every edge that I see coming from a node, right? We start the list by first outer iteration, iterating through all the nodes. Let's iterate, index the nodes 0, 1, 2, 3, 4, 5. That's the outer iteration. Then within each iteration, each element of that array has a list associated with it. That list stores all the outbound edges from that node. So for example, starting at node 0, array index 0, the outer iteration. This node has which outbound edges? It has outbound edges to 1 and 4, right? So we need a dynamically sized list to indicate that this node has 2 outbound edges. So let's do some kind of analysis, right? Intuition or kind of study here, right? If a matrix is extremely dense, what do I mean by matrix being dense or a graph being dense? If a graph is dense, what's the best way to store it? So what does it mean for a graph to be dense? Yeah. Yeah, so for every node, you can count on there being a lot of edges, right? If that's so, what's an example of a dense graph? Yeah. So suppose that you are in a high school class, right? Classroom. And there's 30 people in the classroom, and everybody knows each other, right? I know of, it's like a 30-person classroom, I know of who that person is. You can count on the fact that the knowledge of each other, that's a pretty dense graph. Now, on the other hand, so if it's a dense graph, like what's a good representation for a dense graph? Adjacency matrix, right? So you basically want to, you can count on almost every element having some information, either the fact that the edge exists or there's a weight associated with that. So it makes sense to store it as an adjacency matrix. On the other hand, if a graph is very sparse, right? What does it mean for a graph to be sparse? Yeah.
There's a lot of like empty data basically, like there, I guess in this case, like there would be a lot of nodes that don't connect outbound to other nodes.
So a lot of nodes that don't connect outbound to other nodes, right? So here, this graph is pretty sparse, right? This picture, this matrix corresponding to, and let's see, this graph here, pretty sparse, right? It corresponds to this graph here, where if you look at, say, node 12, node 12 is not very much connected to most other nodes. And so for a graph like this, it makes a lot less sense to use the whole adjacency matrix to store it, right? So what are a couple ways we can compress this graph representation? Yeah, so you could just go through and list all the edges, or do the linked list, right? Do the adjacency list representation, right? So there's this trade-off here of when it makes sense to use the matrix representation, when it makes sense to use an edge list, when it makes sense to do the list representation. A couple other things provided in the PA2 directory. So there is an example file for a binary search tree, which is basically an example of a data structure implementation. So we can navigate to that. So BST, we're doing BST here. And we've got the code provided for binary search tree level order traversal. So first of all, let's take a look at this, right? So if I have this graph, and I wanted to do a level order traversal, what would be the resulting traversal order? Yeah.
You start at the top, so you go like 7 to 4 to 0 to 6 to 2 to 5 to 3.
So kind of trick question, right? Was it enough information I told you? I just want to do a level order traversal.
You have to say like bottom or like top.
Sure. So yeah. So to be very pedantic, right? I want to do level order traversal. Okay. So level just says we're going to go level by level in terms of the depth of the tree. But there's another choice, right? We could say, is it bottom up or is it top down, right? So suppose I'm going to do a top down. We're going to start at the root, and each printout is going to be deeper and deeper into the tree. So we're going to do a top to bottom level order traversal. And there's one final piece of information. What else do we need to know? There's one more choice we have to do. Top to bottom, yeah. Yeah, left to right or right to left traversal, right? So now, finally, that's enough information. I want to do a top to bottom, left to right traversal of the binary search tree. So then what would be the printout? 7, 4, 0, 6, 2, 5, 3. Yeah, left to right. Right, this is all review, right? Is there anything that I mentioned just now that needs a little bit of clarification? Happy to do so. Just let me know. Okay, so suppose we're going to do this level order traversal. Right, so here's the level order traversal. How will we do such a traversal? Can we just read off of the binary search tree and do the traversal? I'm getting at, so this is what kind of data structure do I need to do top to bottom, left to right, level order traversal? Yeah. Yeah, we need a queue. Why do we need a queue? And what's the queue property? What is a queue versus plain old linked lists or stacks? Yeah.
Because you're doing level order, you're doing a breadth first search kind of, like in a sense, where like
Yeah, okay, so good. So another term for level order traversal is we're going to do a breadth first traversal or breadth first search. Good. So those are all tautologies right now. We're just saying the same thing multiple times, right? Okay, level order, breadth first. But what is the critical reason, right? It could be obvious or it could not be obvious. Why do we need a queue to do so? Yeah.
Because it's first in, first out, so like because of the order that's going in right here.
Okay, so we have more information now. A queue is first in, first out. A well-functioning queue should be first in, first out. All right, so that's more tautology. We just gave the definition of a queue. But how do we link the two things, right? I want to do a level order traversal, so I need to do a first in, first out data structure. Can we point to like this? Point to the picture here and say exactly, yes, that is why we need a queue. Yeah.
Is it because you want to put like each parent node inside the queue so that when you cross out a node as like a parent, like you saw the parent take out the queue?
So all of getting warmer, right? So something about parents and crossing things out and traversing the queue. I'll give you all one more kind of shot to refine the discussion, and then we'll talk about it. Yeah.
Sure. So you include a parent, then you would dequeue it, printing it out, and then you would include the left child, and then you would include the right child, and then you would continue doing that until the queue is like empty.
So good. That's also good. So you get the parent, you enqueue the left child, you enqueue the right child, and then pop off of the queue, right? So we're getting that's exactly correct in terms of what you have to do. But what's the deeper intuition why you have to do that? Yeah.
I guess they want you to follow a specific order. That's what happens.
We have to follow a specific order, so we have to use a queue. Right? So the whole point here, and maybe the point I'm making is very obvious, but I'm not sure, right? The whole point here is at any given moment, your program grabs onto exactly one piece of data, right? So at any given moment, I can only make decisions about the node I'm considering. I have this node, it's 7. It has a left child, 4. It has no right child, right? This struct that I'm holding onto, this object that I'm holding onto, I can examine its containing and contained information inside it, but I can't delay decisions until later, right? So I have a left child. I need to put that information about the left child, the pointer to the left child, somewhere so that I can access it in the right order later, right? So a concrete example here would be, say, I have a pointer to node 4, right? I have a pointer to node 4. I'm looking at node 4 right now. Node 4 has a left child and a right child. And I need to make a decision about that information about that left child and the right child immediately. But I can't, I need to delay that information until later because at the same time, node 4 could have a sibling node that has to come first, right? So there's a sequencing of the information here. So that's why we need a queue. I need to take this information about the left child and the right child, put it on the queue, and then tend to more urgent nodes that need to be printed, such as a hypothetical sibling node of node 4, right? That's the deeper reason, or kind of potentially obvious reason, why we need a queue. Okay, so good. So we're going to take a look at that BST, that queue, examples of data structures. And we're going to go look at the source code for BSTLevelOrder traversal. So right off the bat, right? So the first things that we see is now we have examples of including header files that are not the standard headers. So these 2 lines here, what's the visual cue that tells me something interesting is going on between these 2 lines? Yeah.
One uses like the carrots and the other uses quotation marks.
So one uses the carrots, the other uses quotation marks. Any guesses as to what that is supposed to do? Yeah, back there.
So you're reading a file. You're putting a path, and you're trying to find a specific file which contains functions that you use.
Good, right? So maybe another deeper question, right? So we've been importing standard libraries all this class already. Standard library, standard input-output, standard Boolean, standard math, libmath. Where are those things residing, right? Where do they come in from? So let's refine the word, right? So you said the angle bracket ones, the standard ones are online. What do we mean by online? Right, so yeah, go for it. They're installed alongside with the compiler for C, right? As part of the definition of the C language, for the version of C that you have, when GCC was installed, all these standard libraries were payloaded with it. And you can look up where these header files by saying locate standardIO.h, and it will tell you on the Linux machines, based on your user settings and where to look, it tells you that there's all these versions of standard input-output that are included, along with some bogus ones too, right? So standardIO.hpp, that would be, say, a C++ installation. So there's several of these that it chooses from. It will be, the one that's actually used is the one that's installed alongside GCC. So how do we know which GCC we're running? When I say GCC, this compiler that the makefile invokes, where is that? So we can do a couple things here, right? We can locate GCC again, and it will tell us, okay, on the standard paths, there's all these locations where various GCC-related things are installed. You can inquire exactly which GCC you're invoking by saying which GCC, and it tells you the GCC, when you say GCC, that really is invoking this one installed at a standard path of user space code, binary applications, among them the GCC application here, right? And alongside that, when you include standard IO, it is including the one and the user space applications include code standard IO.h. Okay, so those are standard imports, standard includes. What about this one? So the quotation marks one. Where does it locate where this is living? Yeah.
It might search within the directory.
Yeah, so it will just search from where you are invoking GCC, right? So when I say GCC bstLevelOrder.c, it sees that, okay, I want to include this header file, bst.h. Okay, next question, right? So why have I pulled all this code out into a separate header file, bst.h? What's the rationale for having a header file? Yeah, back there.
You want to reuse some code and include the file in multiple other places.
Yeah, so I want to reuse this code, so I just pull it out, refactor it, so that once I've built this BST, I can use it later on, right? So for example, a hypothetical reverse order traversal, or some other order traversal I want to demonstrate. All of those are all BSTs. The code is reusable. So here is that binary search tree code. You should study this kind of in your own time, but again, we have our structs. So this time around, there's something new going on here. So we have a new keyword here called typedef, right? So here, typedef, what this is doing is it's kind of like an alias. It's giving things a nickname. It's creating a nickname for this thing called a struct. Right? Again, what are structs? Structs are just sequences of data with a well-ordered set of types, which tells us how much space it's needed to store in memory. And we're giving struct BSTNode, this particular kind of struct, a nickname. We're just going to call it plain old BSTNode. So now, we can now, instead of always having to say struct BSTNode, we can just say BSTNode. So here, notice in this code here, I'm simply saying the size of a BST node. instead of having to say size of struct BSTNode, instead of saying the size of a struct BSTNode, we're using the nickname, the short name for the overall type. Just again, some syntactic sugar things that are going on here. So we have our BST nodes. They have a key, so the number that's associated with that node. Each has a pointer to a left child, a right child. We have functions to insert keys into the BST node, right? So just some logic on if the node doesn't exist, then malloc the node. If the node exists, if the node exists and the data doesn't match, then we need to push the node into the correct location in the BST, right? So it compares the key that you would want to insert against the value locally. If it's smaller, insert to the left child. If it's larger, insert to the right child. Right? Any questions about this? We've encountered BSTs in previous classes, right? Right, nods. So this is just the C language version of that. The new thing here is, well, this time around, we're required to use malloc and free, right? Malloc is actually still relatively intuitive. When you constructed BSTs in Java, this is really exactly the same as the new keyword. But in Java, you only had to new up objects. You never have to worry about deleting objects. Here in C, every time you have a malloc, there has to be a corresponding free. Right? So this here, down here, this is really just the corresponding code there of freeing the whole tree. Quick quiz here, right? Just to study this code a little bit. What kind of traversal is this? Deletion. Yeah.
Bottom up and just going from right to left.
Right, so it's a bottom up, right to left. So correlating the code there to our picture that we built. Once we're done with the BST that was built here, what order would all this be deleted in? Yeah.
Be like 3, 5, 2, 6, 0, 4, 7.
Is that true?
Oh wait, no, sorry.
So trick question, I guess it wasn't strictly bottom up. So code on the left and picture on the right. Assuming that we've built this BST this way, what would be the deletion order of this code acting upon the BST there? Yeah.
Would it be 5, 6, 3, 2, 0, 4, 7?
All right, so it prefers deleting right child first, right? So right child of 7 doesn't exist. 4 is right child, okay, there. 6 is right child doesn't exist, so deletion order will be 5, 6, 3, 2, 0, 4, 7 is the deletion order. Right? Again, this is just illustrating, yeah, every time you malloc, there has to be a corresponding free. Okay, so there's the BST data structure in our example. Next thing, right, it includes yet another file. So this other file is QueueNode.h. So let's go take a look at the queue. So here we have a queue, right? And I guess just kind of quick question here, who's actually incorporated using this queue in the assignment? A few hands, right? That's good, right? This was the point, that the queue built here, you're allowed to use it, and you should use it, given that it already exists, to implement whichever graph algorithms that you have for PA2. the first thing that we have to take a look at now is kind of, interestingly enough, why this time around we have to have a definition for struct Q. So let's contrast here, right? So in our code for demonstrating Q, I have Q.c now on the right side. And I also want to pull up our example code for stack.c, right? Stack and Q. They should be essentially duals, or in some ways closely related. So on the left-hand side, I have stack. The handle to the stack is on the highlighted line there, line 50 on the left side code, stack.c. And then on the right-hand side, the handle to Q kind of seems like a hassle. Why do we this time have to have a whole struct associated with it? Yeah.
I think it's to maintain a pointer at the front and the back so that you reduce traversal time. You try to enqueue or dequeue. And you don't really need that with the stack. You can just update the pointer at where it is because you don't edit in the stack from both ends, just from one.
Good, exactly right. A stack, you only manipulate the stack from one end. You push it in, you pop it off. It's first in, first out, or first in, last out, right? Last in, first out. On the queue, on the other hand, by definition, you want to access it from both ends, right? So the number of pointers associated with this data structure, where you should grab onto the data structure, is now fundamentally different, right? And so what's the motivation for having this struct here? Right? Again, what's a struct? A struct is really just a organized way of putting multiple pieces of data together that's meaningful, right? So here, for Q, I need to keep these 2 pointers organized. It never makes sense for me to have access to one of the pointers, but not the other. So that's the motivation for having a struct here, where struct Q is really just a bundle of 2 pointers that have to be put together. Good. So just again, pointing out the nicknaming, the shorthand, the syntactic sugar that we were invoking here too. Type def gives types a nickname. So struct Q has been given a nickname of just plain old Q. That's why over here, we don't have to call it struct Q. The data type now is just plain old, simply one word, Q. Okay, the next interesting thing here. Again, I'd like to put 2 pieces of code side by side for us to study now. Let's now look at these queues, right? So queue and stack, both are linked lists. For linked lists, it makes sense for us to define a linked list node for whatever data structure we're implementing. And so where's the linked list node for stack here? Where on the screen is it? Just to, clarify what I'm saying here, right? So stack.c, for the stack example, I'm going to compare stack and queue again. I've got 2 things that should be very similar. So as kind of a study on code quality and what the code is doing, and also kind of elegance of the code, I want to put these 2 versions of code side by side. I've got the stack, I've got the queue. Both have linked lists. So on the stack side, here's the linked list. Right? This is the linked list element for the stack. On the right-hand side, this is for the queue. And in this case, the linked list is over here, QueueNode. Right? Linked list node, linked list element, they're all linked list pieces. What's the key difference between the 2 things I've highlighted here? Yeah.
That for the data, one is just like digital, other is
Good. So there's a critical thing I've done here, right? So on the stack side, when I gave the stack example, the stack just stored a number. On the other hand here, I'm defining what the I'm defining what the linked list node contains to be yet another pointer. Why is that? Yeah.
You would want to queue things that need pointers to reference them instead of something like ints.
Okay, so one argument, right? This is a subtle thing now, right? So I'll try to say this like carefully. So one reason that you may want to store a pointer here is maybe the thing that you're trying to store the whole time was just a pointer. That's a great reason. What's another reason? Yeah, over there. We can now also store whatever we want. What is this equivalent to in Java?
It'd be a generic.
A generic. What is a Java generic? Have we encountered Java generics before? Some yeses, some nos. Who knows what a Java generic is? Who doesn't know what a Java generic is? So could we give a short indication or short discussion on what a Java generic is? Yeah.
At like the start of your class, use triangle brackets to create generic types. And when you use a type of that generic, you just say, okay, I have an object of this type. And when you use the class outside, you can say, I want, like, for example, a list of strings, a list of paths, a list of numbers, and then
Okay.
like a layer of abstraction for type T.
What's our favorite Java data structure? Just shout it out. What's your favorite Java data structure? Array list. Okay, so let's go for Java array list. Java array list example. So here we go, Java array list. And here we go. So Java array list. I'm declaring a new array list called cars, and that will be constructed as a new array list invoking the constructor. Now, what's this thing here? Have we encountered this additional notation before? Some nods. So what is it? If there's little nods, then yeah, tell me what this is. Yeah. Yeah, so what is the formal kind of phraseology to describe what this is? Yeah.
Call it like the type parameter, generic type, depends on what language you're using.
Okay, it's a type parameter. It's a parameter which describes what type of stuff this array list is storing. Now, how do you think they built this code? Right? In Java, somebody created the array list class. Yeah.
They use like this capital T to denote its generic type when in the method signature.
Okay, so good. So another thing to chase down, right? Array list documentation. The documentation for array list coming from the source itself. It says array list has a type parameter called E. Right? So this means that this array list can store whatever type you wish. You just have to tell it what it is. And how is this being built up? Right? Somebody had to create this library of java.util, right? All this code defining what array list is. And you'll bet that they didn't go and write out every possible imaginable type there is, right? They made this a generic object class, and the genericism here is enabled by pointers, right? So instead of storing the values of what's being put in the array list, underneath it is just storing, array list stores a bunch of pointers. Those pointers can point to data of whatever type you want, right? So what the code here given in the QueueNode.h, this is basically a primitive implementation of allowing you to create generic queues. This queue can store whatever you want. You just have to make sure that you're storing pointers to whatever data you want. Does that make sense? Okay, so how might we use this, right? I've got this queue, so now I have to make sure that I'm storing pointers to whatever I want. How do we make sure of that? Or how do we actually use it then? Right, it's not going to be in this source code file here, not in QueueNode.h. QueueNode.h simply says that here's the enqueue function, here's the dequeue function. When you enqueue and dequeue, the data that you're enqueuing and dequeuing is provided as pointers of generic type, pointers to void, pointers to whatever type you wish, right? So it becomes the responsibility of the user of QueueNode.h, say example, going to be given in QueueNode.c, QueueNode.c here. QueueNode.c, when we enqueue and dequeue, what's being stored in the enqueue function is a pointer, and that pointer points to a allocation of memory given here. And so where should we go look for the corresponding free, right? Every time you see a malloc, that should trigger in your mind, there must be a corresponding free. So where will be the corresponding free here be? Yeah.
When you're like when you dequeue an object, you like free that object.
Yeah, so the corresponding free to this malloc here would be right where we dequeue. So every time you dequeue something, the corresponding free is right there. Free the pointer that was dequeued. Okay, anything I can say here to clarify what's going on here? What's the key points? Key point is here is how you make a generic queue. So the queue no longer stores a fixed data type of some sort, but rather by storing just pointers to whatever you wish, so long as whatever you wish is allocated on the heap, you can create a queue of whatever type of object you want. Yeah?
If dequeue frees the memory in the method itself, do you also have to create a queue where you call the method?
So say that again.
Like dequeue frees the pointer in the method itself, and would you still have to free the pointer in the file that you call from, that you call dequeue from?
So your question, I believe, is this, right? So in this version of code here, we make free here, right? I put free after accessing the data outside of the dequeue function. I believe what you're suggesting is, well, you can imagine a implementation. You can imagine an implementation where freeing takes place as part of dequeue, right? As part of dequeue here. So would that make sense? Yeah.
Yep, because the pointer's in the main method, and so you can't really access that from the dequeue method. You'd have to first free the pointer that's in the dequeue method, and then free the pointer that is in the main method in order to make sure that there's nothing left.
So maybe I'll confuse you all some more, right? I'll ask this question to make everybody even more confused. There's a free here in dequeue. Is that the same free as this here? Yeah.
The free inside of the dequeue method frees the QueueNode, or it frees the frees the QueueNode, and then the one in the main method frees the pointer
Good. So you should think of these things as basically nested data structures or nested data types here, right? Here in QueueNode.h, this deals with the queue. The queue consists of QueueNodes. Those QueueNodes have to contain two pieces of information. One is the data that the node should have and a pointer to the next queue node. So here, when we free this free, if you trace through what the code says, this free is dealing with freeing that queue node, right? The container for the data. Outside here, this free pertains to the data that the queue keeps track of. What's the data? It can be whatever you want, right? In this case, the data that the queue deals with is a bunch of characters, right? Just as this example here, right? Another kind of subtle, I guess, rule of thumb is you should group code that deals with the same idea together, right? So the malloc taking place on this line is creating a box for the data you want to keep track of. And that is associated with putting that data on the queue here. And so it's a good practice to make sure when you dequeue, the corresponding free of that box is nearby. Okay, so this was a detour around to take a look at a subtle thing here, dealing with queue and creating a generic queue, right? And you can use this code to queue up whatever you want for programming assignment 2. All right, so this whole time we've been talking about a queue. So how do we make use of that in BSTLevelOrder traversal? Right, so BSTLevelOrder traversal, the code, the driver code here, the C code, basically puts all these ingredients together, right? It creates a queue. First of all, it creates the BST, right? So it reads through the file. While the file is not empty, put every list of, every item in the list in the input file onto the BST. And once the BST is constructed, you can close it, right? So at this point, you can think of this picture, we've made this BST. What it wants to do next is then to perform a level order top to bottom, left to right traversal, which requires it to invoke a queue. So there's your queue. And it grabs hold of the top of the BST here. And while the BST is not iterated through, right? So while the BST still is not traversed all the way through, every node that you get, what you should do is print the name of the node, put the left child on the queue, put the right child on the queue, and you're done for that node. The next node comes from your queue. You grab the front element off the queue at that moment. Does this make sense? So one thing that sometimes we did before is we actually ran a simulation of this code. Is that helpful, or do we know enough from data structures that that should be okay? So I see nods here. What does nods mean? Yeah.
I think we should be okay, at least for me personally.
Okay, right. So the queue keeps track of what's coming on next, right? Good. So that's the example of using a queue on data structures. And more importantly, having two data structures interact, right? One data structure is a BST, other data structure is a queue. So next thing going on here, right? So we've done a breadth first traversal. What's the counterpart to breadth first? Yeah. depth first. What are other names for depth first traversal? Yeah. In order, reverse order, right? So what is a in order traversal of this graph going to give? Yeah.
I think it would give 0, 2, 3, 4, 5, 6, 7.
So in order here would give 0, 2, 3, 0, 2, 3, 4, 5, 6, 7. That's right. And reverse order is just the reverse of that, right? So trivially, it just gives you 7, 6, 5, 4, 3, 2, 0. So let's study code for that, right? So the key difference, again, level order, breadth first versus depth first, in order, reverse order. The types of data structures that are needed to keep track of state are very different, right? So breadth first, that deals with queues. For depth first, that deals with stacks. Right, so let's go and take a look at an example of a depth first traversal. So in this example here, this is a depth first traversal. Let's clear up our environment. So here we have a depth first traversal. Good. Next thing next is the BST loaded up from the included file as before, right? So this is why I extracted BST into a separate header file so that it can be used also in this example here, BST reverse order example. And the way that this code works, again, I load up the input file. The input file has a list of numbers I'd like to put on a BST. And while the input file is not done scanning through, I put every node into the BST. And then we're done, right? That file is closed. We're ready to demonstrate we know how to do a depth first traversal, which is implemented here. So depth first, I'm doing a depth first traversal. What I do is, while the BST is not empty, what I do is I go to the right child, I print locally, and I go onto the left child. Okay, so here's the first trick question, right? So I've narrated up to this point, and there's something missing here. What's missing? So this whole time, right? This whole time, the BST level traversal example code, we went through this whole process of creating that queue data structure, which we use to explain generic queues. And that QueueNode you can use for the other parts of PA2. And now I'm here demonstrating a reverse order traversal, which we understand any reverse order traversal, it needs a stack. But where's the stack in this code? Yeah.
Is it the call stack?
So what do you mean by the call stack?
Like for every, when you're executing a program and you call a function, it places that function frame onto the stack in memory.
Mm-hmm.
And so in essence, we're kind of using the actual memory stack as a stack.
Good. Does that make sense to everybody? It bears repeating, right? Where's the stack in this code? I never, if you look at this code, literally there's no mention of the word stack, right? And this whole time I'm saying in order to do a depth first traversal, I need a stack. And where's the stack here then? the stack is piggybacking off of the function call stack. We're using recursion in place of explicitly creating this stack here. Any questions here? So if I said, all right, so instead of implicitly using the function call stack, would it make sense for us, right? Would it be possible to actually write out the stack? Yeah.
Yes.
Sure, right? So we could actually go and import stack.h, can extract out the stack code, and instead of piggyback off of recursion, as in this code here, we can write it out to use a stack that we create as a data structure to implement this code without using recursion. Okay, any questions here? So what's the key point here? Right, we've done this whole detour onto binary search trees, which are not part of PA2. So what's the point here? How does this help us finish PA2? Yeah.
Because while there aren't binary search trees, the idea of using queue with breadth first and stack with depth first can still apply to the graphs that we're analyzing.
Yeah, each of the parts of, most of the parts of PA2, they're just traversals of graphs, which you either need to choose, do you want to do as a depth-first traversal or a breadth-first traversal? So every place here where you need to do a traversal of these graphs, you can piggyback off of the code given as part of the BST example to put nodes onto the queue, take nodes off of the queue, put things onto the data structure, and so forth. Okay, all of this is good. Any closing thoughts on PA2 before we move on to new content? Let's see. Good. Okay. Okay, so we have some time now to review where we left off on Thursday in terms of representing integers. Okay, so where we left off on representing integers, right? So this time around, compared to before in Java, we want to have a way to represent negative integers. And we studied a couple design options, right? One obvious option is to just say, well, let's dedicate a whole bit to store whether or not it's a negative number. There were some positives and negatives of that approach, pros and cons. So some pros of using the sign magnitude approach, dedicating a whole bit just to represent negative numbers. It's intuitive. It's very similar to how we write down negative numbers in human readable decimal number system. One of the cons, right? One of the cons is we have duplicated zeros. Right? We saw that there's two representations of the integer 0. There's +0, -0. That was one con. And what was the final biggest drawback of that approach? Yeah.
Addition doesn't produce the output that we are expecting.
Yeah, no simple rule for addition, right? For addition, we tried doing addition on the binary numbers in the way that we're used to, bit by bit, right to left, from the least significant digits to the most significant digit. It did not generate meaningful results, right? So we struck that out and we moved on to the next approach, which is one's complement. Right? The idea for one's complement is a couple design principles, right? In order of design principles, first things first, zeros should look the same way as we're used to, right? The encoding for 0 is still 0, 0, 0, 0, 0, 0. The encoding for 1 is still what we're used to, 0, 0, 0, 0, 0, 0, 0, 1. Right? Those things we're adhered to. Third design principle, we want the leading bit to tell you whether or not a number is positive or negative. Right? So if the leading digit is a 1, we want that to indicate that the number is negative. And so to carry through all of these design ideas, the basic idea of one's complement is, well, what if we just, in order to encode a negative number, the rule is you flip all bits, right? You flip all bits. And what were the pros of this approach? Yeah. Also intuitive. Addition works, but there's a strange rule, right? So for one's complement addition to work correctly, you can still add from the least significant bit all the way to the most significant bit. The one subtle new rule is if your addition creates a overflow, a carry bit, that carry has to come around and get added back. Right? This is called a wraparound carry. So those were the pros. Cons. So cons is exactly that. Right? Cons was exactly the issue of there's this matter of the wraparound carry. Yeah. Yep, and then still in one's complement, there is the drawback of there still is a duplicated number of zeros. Subtle thing here too. These two facts are deeply intertwined. How so? Right? If you really think about it, the fact that the representation has a duplicated number of zeros is closely related to why you need to do wraparound carry. Right? The reason is one of your representations has been dedicated to -0, and so when you reach the end of the representation capacity, in some ways you're off of your expected value by 1. Right? That's kind of the deeper reason these two concepts are actually closely related. Okay, so all of this motivates the actually useful and important representation here. Right? All of this is developing the downsides of other approaches to show that the ultimate way that all digital computer systems represent numbers are all using 2's complement representation for negative numbers. And the basic rule for the 2's complement representation is that in order to make a number negative, you flip all bits and add 1. Right? So here it's helpful for us to replicate the notes that we had before. Right? So 2 2's complement representation, design principles, right? Design principles, same thing. The representation for 0 should be as expected. The representation for +1 should also be natural. So we were motivating that in a 8-bit representation, 0 looks like 0, as we're used to. +1 looks the same we're used to. The third design principle is we want to use the leading bit, right, as a quick indicator if a number is negative. So to build out the set of rules, what we tried now is, whereas 1's complement was just flip all bits, maybe instead of doing flip all bits, say here is flipping all bits, that's flipping all bits, we also add 1. Right, so this time around, when we flip all bits for 0, for example, right, flip all bits for 0. There, I flip all bits for 0, and I add 1, which is the rule for negation. Right, there I flipped all bits for 0, I add 1, we come back to the representation of 0 again. Right, so this time around, 0 has exactly 1 representation. It's just 0. We then talked about the largest positive number, which is largest positive number, design principle 3, right? The leading bit should tell you whether or not the number is positive or negative. So the largest positive number will have a leading bit of 0, indicating positive. And the remaining digits are all just 1s. Right? And this representation here, this is the value 127. Largest magnitude negative number, again, design principle 3. The leading bit should tell you whether or not a number is negative. So the first bit should be 1, and the most negative number is going to be this one. Right? And how do we interpret what this value is? Yeah.
The first bit being on the left. So like the 1 is storing like a negative 128, and is not, you're not adding anything from the other bits to it, so it's just negative 128.
So this representation here is going to be the value negative 128. And we can check various things here to make sure that that makes sense. Right? One thing that should make sense is the representation for negative 127 should be what we expect it to be. Right? So minus 127, we can create negative 127 by taking the representation for positive 127 and flipping all bits. Right? So let's take positive 127, flip all bits, and add 1. Flip all bits. And add 1. Right, so we can see now there's no problem. Negative 128 and negative 127 are adjacent to each other as expected. And the gorilla in the room here was that in this representation, the most negative number and the most positive number are not the same magnitude. Right? We sacrifice one of the positive numbers to encode 0. Or another way to think about it is we took what would have encoded negative 0 and used that to represent negative 128. Okay, one more property that we wish to check. Right? One more property that we wish to check. The most important property that ruled out the previous 2 designs is we want to see that addition makes good sense, right? So what is the rule for addition here? we can try some examples. Suppose I want to take negative 128. I want to do negative 128 plus 127. What's our expected value? Negative 1, right? So let's give this a try now, right? So negative 128 is 1, 0, 0, 0, 0, 0, 0, 0. Largest positive number is 127, which is what I want to add it to. So 0, 1, 1, 1, 1, 1, 1, 1. Addition, as we expect. Addition as we expect, bit by bit, what will it be? So column by column, right to left, LSB to MSB. We add all these things up, 1, 1, 1, 1, 1, 1, 1, 1, and there you go. The expected value, negative 1, is the correct representation, right? So in 2's complement, the final really nice property is addition works exactly as we are accustomed to. There's no separate additional rule about wraparound carry. It works fine. So that's one way to arrive at 2's complement representation. Another kind of just rule of thumb that you can use to decipher this is you can just think of the leading bit as a weight of a large negative number, right? And that still would make sense. The encoding, you can treat it as that. Okay, so what we'll do is on Thursday, we'll come back and we'll talk about how to represent fractional numbers, right? So how do we represent numbers that are less than magnitude 1?
Hello.
Hi.
I just have a quick question. So I was wondering if the autograder's test cases are the same as the ones that are in the file for like at least the first 5 for solve maze.
For solve maze, the autograder starts randomizing. For solve maze, the autograder starts randomizing only starting at test case 6. So all the way from 0 through 5, they are always fixed test cases.
Okay, just because when I like run it with with test case 0, I get a solution, but then as soon as I do the autograder, it doesn't even get past test case 1 without saying there's.
So how did you compile this solve maze here? Did you? So if you invoke make to make solve maze, and then you run.
Yeah, I do make and then I run this line.
And then the expected output is doesn't right. You don't know the known expected output, right? So it's just that 0, 1 should be a solution to it. And then the autograder is saying that there is a address sanitizer issue. So make clean and make again.
Clean?
Yeah. Make. And run your example again. And run the autograder. Okay, so let's see, what is the bug here? So it's saying that there is a heap buffer overflow on line 43 of your code. So could you zoom in and yeah.
Here?
Yeah, just make the code bigger so I can see. I mean, there's some way in which you're, yeah, some way in which the there's array access overflow here, right? So line 43 is saying that you're accessing the parent's array with the index source. It's saying that there's a heap overflow from address sanitizer. So what you should do is you should figure out what's the capacity of parents there, what's the array size, and then also print out what's your index that you're accessing at, right?
Okay.
So just basically you're trying to debug a array index out of bounds error here.
Okay. So I'll just use like print statements, I guess.
Yeah, take a look at that.
Alright, thank you.
Hi.
Hi, just a quick question.
Yeah.
Where can I find like information on